I'm just worried about someone calling me and kicking me out of the recording, so let's make sure that's going, and I think we're good. Okay, so logic is the course that we're doing here. Have you guys all had me as a teacher before? So I don't need to do any weird introduction stuff. I don't need to yell at you to make sure you understand it's okay to talk back. And this isn't one of the classes where I stand up here and talk and you just sit there and listen and don't respond.
You know, that really hurt my feelings.
What? Come up in front of the camera and say that to me. This poor snowflake over here got a little close to the heat. Okay. So, since you guys don't have the logic book yet, I sent that to you, so you haven't had an opportunity to read any of it yet. So you'll read that material and we'll cover it. I'm not sure how much we'll be able to cover a day. Based off of what I did in the geometry book, when we did geometry, we got through roughly 20 pages each class period, so that's a ballpark for how much you want to be ahead. So before next week, you're going to want to read the first 20 pages of the book I just sent you, roughly speaking. Make sense? And obviously try to get to a logical stopping point. I'm not just going to end in the middle of a section type stuff. Now, the logic textbook that we're using, it's not great, but the reason that I'm using it is because it's one of the few textbooks I could find that's doing what I'm trying to do. What this class is intended to do is to give you a logical foundation for mathematics. Does any part of what I just said sound weird? A logical foundation for mathematics. So we want to start with our logical foundations and work up to foundations of mathematics. Now for you guys who haven't done, you've still done some courses that were fairly rigorous, like the geometry course that we did. You start out with premises and you work your way up proving things from those premises, and that was fairly rigorous. For you guys that did discrete math, we did a very similar thing. So one of the things we talked about a lot in discrete math is we started out with the natural numbers, we started out with addition, we started out with multiplication, and we went from there. Or was that calculus? Or was it both?
No, it is both.
It's probably both. Okay.
We defined,
You defined the set.
No, in calculus we defined the natural numbers. So it was just in discrete math.
Yeah.
And we defined them a very different way than we would in discrete math where we construct them. So we never defined those things in discrete math, and there might have been a question weighing in the back of your mind, what exactly are these things? How do we define these things? How do we prove these things? And so this class is meant to work up to those foundations. So we want to work up and we want to be able to build the natural numbers, and we want to be able to define what addition is and what multiplication is, because then we know how to take it from there. We know how to define subtraction in terms of addition and division in terms of multiplication. So that's that's kind of the gap that I'm looking to fill here. So we need to go from everyday language to our foundations of mathematics, and we need logic to bridge that gap. Make sense? So logic is a piece that we start with that takes us from our ordinary language to very precise statements. I mean, in short, what would someone define logic as? They loosely say it's the rules for going from true statements to true statements, or the rules for how you can derive a true statement from a true statement. Probably not even true. The rules for how you can conclude statements from statements, probably something to that effect. So we need to start out with what's just language, which is going to be somewhat vague. Pick pieces of it that are precise, that we can get well defined, and then with those pieces work our way up to the foundations of mathematics. So that's what I wanted to do. The author, he's not great, but it's been a pain for me to find a good textbook that does exactly what I'm looking for. What we're going to do today is a teacher that did a really good job was the author of this geometry book that we used last time. Now, he wrote this for high school students, so it's meant to be a high school level run-through of logic, which is what we're going to try to get through today. So we're going to try to run through logic. Then when we start the textbook next week, it's going to be a reset and a much slower, more thorough going through of some of the exact same stuff. Make sense? Okay. So where I like to begin every conversation of logic is a brief conversation of reasoning. And I've probably had this conversation with everyone in this room already, but it's always good to review, make sure that these things make sense in your head. So you all know what it means to give your reason for a conclusion. You come to some conclusion, and the reason is how you justify that conclusion, right? And roughly speaking, there's three types of reasoning. There's deductive, inductive, and abductive. So deductive reasoning is the reasoning that we use in mathematics. It's the reasoning of a logical implication, for those of you who understand what that means. It's the most valid type of reasoning that we know of. So here's an example of it. If x equals 2, then 2x equals 4. Right? This is our conclusion. This is our premise. We're saying if this is true, then this is for sure true. That's deductive reasoning. Another common example of deductive reasoning is, the common one that's given is, all men are mortal, Socrates is a man, therefore, Socrates is mortal. If all men are mortal, and if Socrates is a man, then Socrates is mortal. That's another form of deductive reasoning. If those two premises are true, there's no question in your mind that Socrates is mortal, right? If x equals 2, there's no question in your mind that 2x equals 4, right? Okay, inductive reasoning. Inductive reasoning is the reasoning of generalizations. It's when you observe something over and over again a bunch of times, and then you generalize that phenomena. So, an example of it is, if I let go of this, what's going to happen?
It's going to hit the floor.
It's going to hit the floor. It's going to fall. It's going to hit the floor. Why do you think that that's going to happen? It's not because you stayed up late one night and you came up with this big elaborate proof starting with some great premises and came to the conclusion, that will always happen. It's something that you're concluding just because every time you've watched an object fall, it's hit the floor. Could we imagine some weird possible scenario that I let go of this thing and it doesn't hit the floor? You couldn't? What if there was an object flying through space really close to us and was just far enough away that the instant I let this go, its gravity was pulling on this thing at the exact rate that the Earth's gravity was pulling, and I let go and it just stays there? That's possible. Right? But it's not very probable. So once you get to inductive reasoning, you're reasoning with probabilities. And it's the reasoning that all of science is based on. That's what the scientific law is. It's we've observed this a ton of times, and so now we're going to generalize it and call it a law. Make sense? The third type of reasoning is abductive reasoning. This is kind of the inverse to inductive reasoning. Inductive reasoning is you observe a bunch of phenomena, and you create a generalization from it. Abductive reasoning is you're using your generalizations to reconstruct a specific phenomena. Right? So you've probably all had this experience. You're walking outside and you feel a drop on your hand. One of your conclusions might be, it's raining, right? Not necessarily. Maybe James is walking next to you and he likes to sprinkle a bit when he talks, and he was talking and he got you on your hand. That's possible. Maybe someone's messing with you and just threw like a drop of water. Who knows? There's a lot of things that could have happened. A common place where abductive reasoning is used is in history and in a court of law. So we have to take what we know about people when we're reconstructing history, take what we know about people, take what we know about documents, take all these scientific ideas that we have, and try to reconstruct a scenario or a life or whatever the historian is trying to do, reconstruct what happened. A court of law, the example I like to give is the little kid with the cookie. So, say there's a toddler, you leave a toddler in a room with a chocolate chip cookie within reach. You walk out of the room, shut the door, stand outside the room for 5 seconds, walk back in the room, the cookie's gone, there's chocolate on the child's face. Conclusion, the child ate the cookie. Now, is that necessarily true? Is it true that every time a toddler's been left in a room that they've eaten a chocolate chip cookie? No. So you come to that conclusion, but there's a lot of things that could have gone on. For example, Big Brother could have been hiding in the closet when you left the room. He could have come out, eaten a chocolate chip cookie, saved the chocolate chip, smeared it on the kid's face, went back in the closet and hid. And then you come in and get mad at the toddler. Poor kid. It's possible. So this type of reasoning, we often come to conclusions beyond a reasonable doubt is the terminology that they like to use in court. When you prove it beyond a reasonable doubt, that's sufficient. Because you can't come up with a deductive proof that the child did it, and you can't come up with an inductive proof, or a proof only based on inductive thinking that the child ate the chocolate chip cookie. And so, you're left with this. So, the nature of the field determines the reasoning that you use. Now, it's important to note that every historian also uses science and also uses math, and every scientist also uses math. A mathematician does not use science, and a scientist does not use history. Right? The physicist doesn't consult his history textbook to determine physical phenomena. Will this fall? I don't know. Let's see what Ben Franklin had to say about it. When he dropped a marker, did it fall? That's not how they do it. Right? You test it right there in the lab, you observe the phenomena yourself. Okay. So, reasoning. This is the one we're primarily interested in this class. And throughout logic and math, that's what you're interested in. So now let's start actually talking about logic. To start with logic, you need to start with a specific type of sentences. The author of the textbook that we're going to use calls them truth functional sentences, sentences that you can assign a truth or false value to. The author of this textbook just called them statements. So what's a statement? It's a sentence that is true or false, but not both. Very well defined, no ambiguity there. You know what a statement is, right? Okay. So we have statements and we can combine statements. So we're going to come up with another definition. Conjunction. If alpha and beta are statements, then the statement alpha and beta, so this is a new statement, alpha and beta is our conjunction. Question, just looking at that, is that a good definition?
Yes. Yeah.
What could you attack about that definition? How do you know if this is a statement? So if alpha is a statement and beta is a statement.
Well, it says if they are statements.
Right. Well, it says then the statement alpha and beta is a statement. Just because I can assign truth or false to that thing and truth or false to that thing, how do I know I can assign truth or false to the whole thing? You see?
Yeah.
That's what I was getting at. And we can, and we know how to do that. So I thought I might have younger people, but we don't really have younger people. So everyone here has seen truth tables. We good with truth? You haven't seen truth table before? Okay, so let's go over it then. So on a truth table, so alpha represents a statement like Donnie's holding a blue marker, and beta represents a statement like Donnie's holding a red marker. Okay? Now there's four possible combinations. It could be true I'm holding a blue marker and true that I'm holding a red marker. That's that case. It could be true that I'm holding a red marker and false, or true that I'm holding a blue marker and false that I'm holding a red marker. It could be false I'm holding a blue marker, true I'm holding a red marker, and false I'm holding a blue and false I'm holding a red. And those are all the possible combinations. So when you have two statements that you're looking at, these are all the possible combinations you can have. You can either have they're both true, the first is true, the second is false, the first is false, the second is true, or they're both false. Those are all the possible combinations. So all we need to do is figure out when this thing is true for every possible combination, that will be well defined. So I can tell you if alpha is true and beta is false, is alpha and beta true or false? And you will be able to determine that once we fill this out. So let's do it real quick. Let's fill this out. Let's set up each scenario. The scenario, alpha is always going to be Donnie's holding a blue marker, beta is always going to be Donnie's holding a red marker. So let's set the top scenario. Is it true that Donnie's holding a blue marker and Donnie's holding a red marker?
Yes.
That's true. So in the case where alpha is true and beta is true, then alpha and beta is true. So in that case, it's true. Continue. Is it true that Donnie is holding a blue marker and Donnie is holding a red marker? No, that's false. Right? Is it true that Donnie's holding a blue marker and Donnie's holding a red marker? No, that's false. And finally, if I'm not holding any markers, then it's
True.
False.
false. Donnie's holding a blue marker and Donnie's holding a red marker.
Donnie's not holding a blue marker, Donnie's not holding a red marker.
There's no knots in there. We haven't talked about knot yet.
That just what went through my head. Because of false.
Ignore the right-hand side of where we're at. Okay. So that is the conjunction of two statements and this is how we determine the truth value of their conjunction. Because we claim that this was a statement, so this is how you determine its truth value. Good? Okay. Now you know from everyday speech that there's more conjunctions than just and. What you were told were conjunctions in an English class. So you say, what about when a statement has the word but in it? Right? Sometimes you have and, sometimes you have but. Why don't we have a definition up here for but? So we're going to go on to or, we're going to go on to not, but you're going to notice that we didn't use another conjunction like the word but. And the reason that we can't do this for a word like the English word but is because the English word but is ambiguous. In some statements, it means one thing, and in other statements, it means another thing. So let's try and give an example. Donnie wants to go to the store, but it's raining outside. Means what?
He's not going to, or he's just going to go.
Well, what did you say?
He's not going to go to the store.
Donnie's not going, or Donnie wants to go to the store is alpha, but it's raining outside is beta. Is alpha true?
Yes.
Is beta true?
Yes.
So alpha but beta in this context means
True.
and. So but right now is being used the same way that and is being used. Right?
Okay.
Let me think of an example where but's used a different way. I think the book has some. Shouldn't be trying to come up with these on the fly. Keep jumping to or in my mind. That's negation. Oh, we kind of jumped the gun without going over examples. Let's do some examples and then we'll come back and talk about and. So statements. I told you that a statement is a sentence that is either true or false, but not both. I'm going to read some things, tell me whether or not it's a statement. Let's go back. Go back home. Is that a statement?
No.
But it's false. 2 times 2 equals 5. Is that a statement?
Yes.
Yeah.
No, false.
It's
Yes.
false. It
Yes.
can't be a
It's
statement.
It's a statement.
It's a statement.
Ah, it's a
False.
statement. Because you can call it true or false. 2 times 2 is 4. Statement. New York is a suburb of Los Angeles.
Statement.
Oh, okay. Thursday up tar paper.
Not a statement.
Not a statement. The silliness of speedily. Not a statement. I am the most beautiful girl in town.
Statement.
True.
That's a statement? Is it true or false?
It's up to interpretation, but it can be. It is true or false. It
It's
is
one or
true
the
or
other.
false.
Let me try another one for you. X plus 2 equals 5.
Statement.
Yes, that's a statement.
That's a statement?
It can be true or false.
X plus 2 equals 5? Whoa. Not can be. What's the definition of a statement? A sentence that is true or false, but not both.
So not enough information is
X plus 2 equals 5. Not a statement. You cannot call that true. You cannot call that false.
What was your other one? Oh, 2 times 2 equals 5.
And that has in it what we call in logic a variable.
Well, you can call, if you're the most beautiful girl in the world, you can call that true or false.
Well, I am reading what's on the paper, but the statement, I am the most beautiful girl in town, depends on who I is in the sentence and
Variable.
what town is in the sentence.
That is so weird.
So yes, there is a way that you could determine the truth of that with more information, just like x plus 2 equals 5. With more information about x, you can determine if it's true or false. But as is, you cannot call it true or false. That is not a statement. Okay? If I don't get a good night's sleep, I can't pass the examination.
Statement.
It's a statement.
Yeah.
You guys get to just let him say that?
That's a statement.
Does anyone have the courage to tell the truth in here?
Yes, it's a statement.
Then we'll let it be. Okay. So then we get to, let's see, what was he doing here? Okay, let's go over some more. I can't go to the dance because I have nothing to wear, my feet hurt, and I can't dance.
That's a statement.
That's a statement. A triangle has 3 equal sides if and only if it has 3 equal angles.
Statement.
That's a statement. Jones is a mathematician and Smith is an engineer, while Brown doesn't work at all.
That's not.
That's a statement.
It's a statement.
That's a statement. There is one and only one line through 2 points.
Statement.
Either I will marry you or get a new job.
Not
That's a statement.
That's a statement. 2 lines either intersect or are parallel.
Statement.
statement.
Okay.
Wait.
I will marry
Go back
you.
one. The one that starts with either.
Either I will marry you or get a new job.
That's not true or false.
I will get a new job is true or false.
Yeah, the part's just as worded.
I will marry you is true or false.
Okay.
Oh, I lied to you guys earlier. I'm getting confused by what the other book's saying at the same time. So remember I told you that those weren't statements? By his definition, they are statements.
What's his definition?
Right here. A sentence that is true or false, but not both. And so I'm reading both books at the same time, and we'll get to variables in the other one and why that was weird. But yes, so he's calling them both statements. Oh, no. In C, if we replace the letter X by 3, we have a true statement. If we replace X by 2, the resulting statement is false. Oh no, he is saying that we do have to know. Sorry, going back and forth trying to follow him. Okay, never mind, so I didn't lie before. Okay? So let's continue. That's enough examples. So let's continue. So now to conjunction. If alpha and beta are statements, a statement A and B is called a conjunction of them. Oh, he doesn't have that conversation I thought that you had here. Okay, I don't think we need to go over examples of and. I guess we can do a couple. 2 times 2 equals 4 and 2 plus 2 equals 5. Is that a statement?
2 times 2.
Yes. Is it a true statement?
False.
No. 3 plus 2 equals 5 and there are at least 52 Sundays in every year. Is that true or false?
That's a statement.
It's a statement.
Is the statement, is it true or false?
There are
It's
52
true.
Sundays in a year.
Yeah. Every year has 52 weeks. And then an extra day.
Hey, shut up.
A triangle has 3 sides and a pentagon has 6 sides.
It's a false statement.
False. Okay. I think we get the hang of when is true, when is false. So let's move on to or. And then he still doesn't have that conversation. I don't know when he has that conversation, but we'll have it when he brings it up. Okay. So we have our definition for a conjunction, and we know what and means in logic. Now let's move on to or. Or we have a problem with because or is ambiguous in the English language. If I say, let's think, Donnie's in his house or Donnie's at school, then in that sentence you interpret it with what we call the exclusive or. You think one of those 2 statements is true, but not both. right? An example of the or case where both of the statements could be true is a college won't accept a student unless they've taken calculus or physics.
Right.
It's fine if they've taken calculus and physics, but they have to take calculus or physics to get into the university. So in that case, we only require one of them to be true, but both of them being true is fine.
Right.
That's what we call the inclusive or. So we need or to be well defined if we're going to use it in math and in logic. And so the or that we choose is the inclusive or. And that's the choice that we make. So in math and logic in this course, or means one is true or the other is true or both are true. Good?
Okay. One is true, or the other is true, or both are true.
Yeah, so let's set up our scenarios. Donnie's holding a blue marker or Donnie's holding a red marker.
True.
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 Alright.
Donnie's holding a blue marker or Donnie's holding a red marker.
True.
True. And then obviously if I just switch markers, it's still true. And if I'm not holding a marker at all, is it true or false?
False.
Just because I'm not holding a marker?
Yeah.
Yeah.
Yeah. That's exactly why. So that's our truth table for a definition of or. And I think you understand we're good with that. We don't need to read more examples. So let's move on to negation. This one's more interesting. Negation. If alpha is a statement, the statement alpha is false is called the negation of alpha. Okay? So, come up with an example real quick. This room is bright. That's a statement. That's alpha. This room is bright is false is its negation. Another way that we could say that is this room is not bright. So typically you introduce the not word when you're trying to negate something. You're saying the opposite of it. You're contradicting what was just said. Make sense? So, if alpha is a statement, the statement alpha is, that's supposed to be is, not if, is false is called the negation of alpha. We also say not alpha. That's another way of saying it's negation. You good with that? So let's do our truth table for not. If alpha is true, not alpha is
False.
false. And if alpha is false, not alpha is
True.
true. Perfect. Okay. Now, we need to have a small discussion about contradicting statements versus contrary statements, and then we'll come back and talk about negation again. So, if I have two statements that contradict each other, what that means is one of those statements is guaranteed to be true and one of them is guaranteed to be false. Let me give you an example. Donnie is wearing socks and Donnie is not wearing socks are contradicting statements. One of those has to be true, one of those has to be false. Make sense?
Well, if you're wearing shoes.
Was I wearing socks?
No. Oh.
Then I'm not wearing socks. You good?
Yeah.
Okay. That's contradicting statements. Contrary statements are statements that can't both be true. Contrary statements would be x is equal to 3, x is equal to 4. Those can't both be true. Maybe one of them is true, maybe neither of them is true. The only thing I'm guaranteed is they're not both true.
But how does that
That
make it
statement
different
seems
from contradicting
worthless
though?
then.
Okay. X equals 3. Its negation, or its contradiction, is x is not equal to 3.
Right.
Right.
One of those is for sure true, one of those is for sure false.
Right.
These are contradicting statements. Contrary statements is x is equal to 3, x is equal to 4.
Right.
Do one of these have to be true?
No.
No.
No, it's possible that they're both false. So when you have contradicting statements,
One has to.
one has to be true, one has to be false. When you have contrary statements, they can't both be true. They might both be false. Maybe one's true, but they can't both be true. Make sense?
Yeah.
So when I say not alpha, I am talking about the contradiction of alpha. So not x equals 3 is x does not equal 3. X equals 4 is not a contradiction of x equals 3.
Right.
It's a contrary statement. It's not a contradicting statement. So when we're talking about negation here, we're talking about the contradiction of alpha. Make sense?
Yeah.
So let's make sure that this is making sense. So all swans are white. The contradiction of that is some swans are black, right?
No.
Those two don't contradict each other.
Those are contradictions.
They are.
Those are contradictions, right?
Yeah.
Because one of those statements has to be true and one of them has to be false, right?
Alright.
Yeah.
No, what if every swan in the world's orange?
Wait.
Then all swans are. So
Which of those are true if every swan's orange? Which one's the true one, which one's the false one?
You got me there.
These two are not contradicting statements, they are contrary statements.
Okay.
These two are contradicting,
Yeah.
No.
right? All swans are white, at least one swan is black.
They can't.
What if they're all orange? What if they're all
What
orange?
if they're all orange?
No,
Doesn't work. Okay, here's the contradiction. All swans are white, there exists a swan that's not white.
Yeah.
Those are contradictions.
There we go.
One of those two statements has to be true. So if I say alpha is all swans are white, and then I ask you what is not alpha, this is not alpha. So nodding a statement, if you'll let me use that terminology, isn't as trivial as it seems at first. When you first think about it, this seems like the easiest operation out of all these. Careful. Negating a statement is not as straightforward as it seems. Good? Feel comfortable with there's a difference between contradicting statements and contrary statements?
Yeah.
Yes.
And negation is talking about the contradiction of the statement? Good. Okay. So let's get a little bit of practice doing that. So let's negate our conjunction. So we talked about just negating a statement. Now we're going to notice some rules for how to negate a conjunction and how to negate a disjunction. Did we ever say disjunction or did I just skip over
You
this?
skipped it.
Sorry about that. Just like we call the anding of two statements the conjunction of those statements, we call the oring of two statements the disjunction of those statements. And what does it mean? What's the truth value when you or two statements together of the resulting statement? You get that from this table. Sorry, I need to skip over that. Good?
Good.
Okay. So, let's look at how we negate a conjunction of statements, and then we'll look at how we negate a disjunction of statements. So, Donnie is the teacher, and the house is on fire. So now let's say that statement's false. Then what statement's true?
Donnie
Is not the teacher or the house is not on fire.
and the house is not on fire.
So let's come up with a scenario where this could be the case. So Donnie is a teacher and the house is on fire. We know that and is false in any of these three cases.
Right.
Let's pick one of them. Let's pick this case. So let's pick the case that we're already... I'm trying to think about how to make this appeal to your intuition. Let's just write what you said, and then we'll see the scenario that doesn't. So you said, Donnie is not the teacher, and the house is not on fire, right?
Right.
You're saying this right here is a contradiction of this. So let's come up with a scenario. Let's say that Donnie is a teacher and the house is on fire. Is this true?
No.
Well,
Yeah,
it
it
could be not right now, but like it could.
We're going to go across the top. Donnie is a teacher and the house is on fire. Let's say that that's true.
Okay.
Let's say that Donnie is a teacher and the house is on fire. Now, is this statement true?
Yes.
Yes.
Is this statement false?
Yeah.
Yes.
Yeah. So far it's working. One was true, one was false.
Right.
All right, let's look at the next scenario. Let's say that Donnie is a teacher and that the house is not on fire. You with me?
Yes.
Is this statement true?
Yeah.
It's
No.
no longer
No.
true.
It's false, right?
Yeah.
Is this statement true?
It's false.
Yes.
Yeah, no.
It's false.
It's false?
'Cause the
Donnie
house
is a
on fire.
teacher and the
Because you
house
are
is not on
teachers.
fire.
So let's pretend it's the current scenario. I'm the teacher, the house is not on fire.
Okay.
Is this statement true?
No.
No, it's
No.
false.
Is this statement true?
No.
Yes.
No.
No.
You are a teacher.
Because the house
Oh,
is
yeah.
And
Yeah,
the
you
house
are a
is
teacher.
not on fire.
No, you
It's
are a
true.
teacher. Yes.
But Donnie is not the teacher is
False.
false.
Therefore,
So is this
this is-
statement true?
No, it's
No.
false.
And this one was.
False.
False.
So they're not,
Negations.
one does not negate the other, or they're not contradicting
What?
statements.
Okay, okay, what are we trying to do here?
We're-
Negate a con-
We're trying to negate this statement. We're trying to find the contradiction of this statement. Right?
Okay.
And you did the very reasonable thing to do. It was a good job. Now we'll do what Levi suggested, and switch and with or.
So or contradicts and is.
Donnie is not a teacher when the house is on fire.
So let's go back to the first one. Let's say that both these are true. Donnie is a teacher and the house is on fire. Is this true?
Yes.
Is this true?
No.
No.
False or false is false. So this was true and this was
I was
false.
about to say true.
Okay, now the next scenario, where Donnie is the teacher and the house is not on fire. Right?
Mm-hmm.
Yeah.
So Donnie is a teacher is true. The house is on fire is false. So this whole statement is
False.
false. Donnie is not the teacher is,
False.
but the house is not on fire is.
True.
Right.
So it's true.
False. True. So the statement's true.
The statement's true because it's or.
Oh,
If one's
or.
true, then the statement's
I
true.
thought you were using and.
No, we switched to or.
Okay.
So this was false and this was true.
So they negate each other.
Now, if we did this scenario where we made Donnie as a teacher false and the house is on fire true, we're going to get the exact same thing. Does that make sense?
Right. Yeah.
And then finally, if both of them are false,
Then both of those are.
if Donnie is not the teacher and the house is not on fire, then this is false and this is true. So those do negate each other. Those are contradicting
Well,
statements.
look at the charts and then you'll see why.
Yeah, so now let's just fill out the chart. So true and true is
True.
true. True and false is
False.
false and true is
False.
false and false is
False.
okay. So now we're gonna not this, right? This is the negation of a conjunction, right?
It's just the opposite.
So we're just gonna not this column. We're gonna take this column and not it. So it's just gonna be false, true, true, true.
Right.
Mm-hmm.
Make sense what I did there? Truth table making sense? Okay. So now let's look at not alpha. Not alpha here is
False.
false because alpha is true, so not alpha is false.
Right.
Following that?
False. True.
True. True.
False. True.
True.
False.
False.
True.
Anyone confused by what we're doing? Feel like the class is just leaving you behind? Okay. So now let's do this one. Not alpha or not beta. So we're oring these two columns together. Make sense?
Okay.
So this one is,
False.
this one is,
True.
this one is,
True.
this one is.
True.
Lo and behold,
Right.
those are identical. So they're logically equivalent.
Mm-hmm.
For any combination of alpha and beta you take, this column and this column give you the exact same result. So not alpha and beta is the same thing as not alpha or not beta. Maybe I should put parentheses here to make it clear what we're doing.
Yeah.
Right.
Sorry. Everyone understand that?
If they're identical, then why did that statement before work?
Because it was not alpha and.
This
not
used to
beta.
be an and.
Instead of
So the first time we wrote it, we had an and here. And that didn't work. Then we switched it
So
to
you're
an or.
saying this works because they're identical.
Yeah, they are logically equivalent. Not alpha and beta is the same thing as not alpha or not beta.
Right.
So that's.
So if I put not
That's so
in front
weird.
of this sentence,
That is so weird.
not Donnie is the teacher and the house is on fire, is the same thing as Donnie is not the teacher or the house is not on fire.
That is so
The
weird.
language is weird there, but does it make
You're
sense?
nodding the whole and statement. Yeah. And it's coming out to not first statement.
We were
or
nodding
not
the
second
whole conjecture. Or conjunction, is that how you say it?
Not conjecture. Let's try and think about it a different way.
Do those?
If I tell you
statement.
that the statement Donnie is a teacher and the house is on fire is false.
You can just time
Distribution.
So I tell you the statement Donnie is a teacher and the house is on fire is false. What do you know? You know either Donnie is not the teacher or the house is not on fire. Right?
Right.
So if I tell you that this is false, then what do you know is true? It's contradiction. If this statement is false, its contradiction is true.
Right.
So I say Donnie is a teacher and the house is on fire is false. Then you know either Donnie is a teacher wasn't true or the house is on fire wasn't true.
Ah, okay.
You
That
know
makes-
this
that does make
or
very
this.
much
Makes a lot of
sense.
sense.
Yes. Okay.
Okay.
Is it clicking?
I
Huh?
think not is the same thing as the contradiction.
Not and contradiction do the exact same thing. Nodding gives you the contradiction. The contradiction of alpha is not alpha. All we did was took not a statement and wrote it a different way. Not A and B means not A or not B. Let's go back and say it with the markers and just try and finish it all together. If I tell you, so now I'm not showing you, and you don't get to see what markers I'm holding, what the situation is. And I say, I'll give you a hint. I'm holding a red marker and I'm holding a blue marker is false. What do you know?
That you're
Either
holding.
you're not holding red marker, you're not holding blue.
You know either I'm not holding the red, or I'm not holding the
Or
blue, or I'm not holding either of them.
Right.
Make sense? So if you know this is false, you know this is true. Because it is the contradiction of this.
Right. That makes total sense.
And what does it mean to negate it? It means to say it's false. Alpha is false. Alpha is false. It's contradiction, not alpha, is true. Is it clicking with everyone? I mean, it's one of those things that's weird until it just clicks and then you're like, oh, duh. Good? Good?
Yep.
Told you to talk. Okay. Moving on. Where were we? Oh, we were negating the conjunction and then we filled out the truth table. Okay. So what about negating a disjunction? And don't look down at my table and try and guess from that. Just try and say the negation of it. Donnie is a teacher or the house is on fire. What's the negation of that?
Donnie is not the teacher and the house is not on fire?
And?
Yes.
Yes. Donnie is not
Reverse.
Right.
the teacher and the house is not on fire.
Right. That makes perfect sense.
Right? And to say it with the markers, let's set it up again. I say the statement that I'm holding a red marker or a blue marker is false. What do you know?
You must be holding both. Or,
No,
You're not
you're
gonna be
either
holding
one
either.
or the other.
You're not going to be holding either.
yeah, you're not holding either.
No, you're gonna just be missing one at least, if not two.
No, yeah.
Let me say it again.
Okay.
The statement, Donnie's holding a red marker or Donnie's holding a blue marker, is false.
You have to be holding either of them.
You have to be holding either of them.
So I'm not holding a red, I'm not holding a blue.
Yeah, you have to be holding.
So I'm not holding a red and I'm not holding a blue.
You have
You're
no
not
markers.
holding either.
No markers.
So I'm holding no markers.
Yes.
So the negation of Donnie's holding a red marker or Donnie's holding a blue marker is Donnie's not holding a red marker and Donnie's not holding a blue marker. Right? That's the only way that the or is false. Is that making sense?
Yeah.
Okay. So let's go through and see that that is in fact the case. We'll put parentheses here again. Sorry about that. Oh, I don't know if I've been driving the point home with you guys enough. The upside down V is and the regular V is or. And negation, not, is a line over with a drop like that. I use these symbols so much I forget to introduce them. So that's not, that's and, that's or. Okay? If we're going along and you see me write the symbol and you forget what it is, just ask. It's just, you'll get to the point where you just subconsciously think about it that way. Okay. Continuing. So, here's all the possible combinations for alpha and beta. We can have they're both false. The first is false, the second one's true. The first is true, the second one's false, or they're both true. Those are all the possible combinations, right?
Yep.
Okay. So, if alpha is false and beta is false, alpha or beta is
False.
false. If alpha is false and beta is true, alpha or beta is
True.
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 Okay? And now we're just negating this column.
Right.
Right, so it's
true,
false,
false,
false.
false.
So true, false, false, false. Right? Okay? And now, what's this?
True,
True,
true, false.
true, false, false. True, false, true, false.
And then this is anding these two columns together.
True, false, false, false.
And they're the same, as expected.
Right.
Good?
Mm-hmm.
So one way I've heard this rule phrased when you're negating is it's the distribution rule.
No, it doesn't work. Tell me about that work.
When you distribute the negation across the statements, it applies it to both and switches it. It makes more sense. I might have just lied a little bit. I think that's when it's supposed to be not. No? I might be mixing two things up in my head, but that's the way I always think about it. I'm distributing the not and switching it from an and to an or from an or to an and. So nodding an and switches it to the nots, or nodding an or switches it to the nots, applying to each one with an and vice versa there. Make sense? Okay. So that takes care of and, or, and not. Now for the hardest logical operator.
Implication.
Implication, implication, implication. So, implications are all over in mathematics. Every proof in mathematics is an implication. And implications usually come in the form of if alpha, then beta. So notice we wrote this and this over here in terms of implications. If x equals 2, then 2x equals 4. Another way we could say that is x equaling 2 implies 2x equals 4. Make sense? Similarly, if I drop an object, then it will fall. My dropping an object implies that the object will fall. Good? Okay. So we talked about that example. Let's look at this example. If Donnie is 20 feet tall, then Donnie is taller than a basketball hoop. Is that true?
Yes.
That is true.
Now notice that this is kind of weird. Is the statement Donnie is 20 feet tall true?
No.
Is the statement Donnie is taller than a basketball hoop true?
No.
Well, you said if Donnie is 20 feet
Right.
tall.
Right. But the point is, notice that alpha in this case was false. Beta in this case was false. Yet we just called the whole statement true.
Because of it.
Yeah.
because
It's an
that's
implication.
what gets you
Because
in
it's an
calculus.
implication.
That's what gets you in all proofs. You sit here and you deal with ifs and you go, you can't just say if this is true. You quite literally can just say if this is true.
Sure you can, yeah. It's perfectly valid reasoning to say that if I was 20 feet tall, then I'd be taller than a basketball hoop.
Right.
Yeah.
There's nothing wrong with that reasoning right there. Even though both those statements are false, the implication is true. And that's what it means to prove a theorem, is to prove that an implication is always true. So let's do a truth table for implication. And this is a tough one that just gets you, but we'll get through it.
Yeah, I'm glad that's.
So alpha will be I'm holding a red mark. No, alpha was the blue, right?
Mm-hmm.
Because alpha's blue.
Mm-mm.
All right, alpha's a blue marker, beta is a red marker. Let's set up the scenario. If I'm holding a blue marker, then I'm holding a red marker. Is that true?
Yes.
If I'm holding
Yeah.
The whole universe right now is just me and these two markers. Nothing else exists. There's no laws of physics. There's nothing else in existence. This is the state of the universe. Always has been, always will be. Me holding these markers as is. Okay? Is it true that if I'm holding a blue marker, I'm holding a red marker?
Yes.
Yes.
That is true.
Because they're both true, right?
Yes.
Because look, they're both true.
They're both true.
Look at his hand.
I'm glad that you used the universe English.
Okay.
That's right.
I understand. There's such a inclination to bring into probabilities based off of personal experience, right? What do the laws of physics allow for? No, we're just saying in the universe where this is the case, always has been the case, always will be the case, there's no change, there's no laws of motion in this universe. Okay, in this case it's true. Alright, now let's have the next case. Donnie's holding a blue marker is true, Donnie's holding a red marker is false. Is a statement, if Donnie's holding a blue marker, then he's holding a red marker true?
No, it's
No.
false.
No, it's false. So this one was true, this one was false. Now, if Donnie's holding a blue marker, then he's holding a red marker.
True.
It's true.
It's true?
Yeah.
Yeah, that is true.
How do you prove it? I'm not holding a blue marker, so how do you say if I'm holding a blue marker, I'm holding a red marker?
Just like Donnie was never
Because
wrong.
they did.
Oh.
So there's two ways that you can think about this. One of these is to think about what mathematicians call a vacuously true statement. A vacuously true statement is when you don't have any cases to check. So for example, if I were to start out one of these if-then statements, if I start out the statement with, if Donnie was a 200-pound purple dragon, then it doesn't matter what statement you put after there, it's always true. It's vacuously true. There's no cases that you could check. It's never true that Donnie is a 200-pound purple dragon. That's never the case. So it's what we call vacuously true. So that's one way to help your intuition. The other way you can try and help your intuition is to think, is it false? So go back to this case right here. If Donnie's holding a blue marker, then he's holding a red marker. Is it false that if I'm holding a blue marker, I'm holding a red marker? No. It's not false?
It's true.
So if it's not false, then it's
True.
true.
Right.
Not false, it's true. Ah, so it's true.
That seems-
So those are two intuitive ways to think about it. I don't know what helps more. Everyone comfortable with that being true?
That's
True.
False. True. And then the last one. If Donnie's holding a blue marker, then he's holding a red marker.
True.
It's true. It's just like the case I set up right here. We had a false statement and a false statement, but the implication was still true. Okay. So implication's a weird one. That's one that will get you a bunch of times. 2 years down the road, when you come across implication again, you're going to have to stop and think for a second and say, wait, when is this true again?
When was Donnie holding that marker?
When he was holding the blue marker.
Exactly.
Okay. So that was as far as I could get without erasing the board. Someone want to give us what the time is real quick?
It's 8:05.
8:05. Okay, so we've only used an hour. I'm just really starting to hurt. Don't know how much longer I can stand.
When is your elective surgery?
I don't know. I got my doctor's appointment on the 17th.
Well, you could sit down and just go through sentences
I
and
can
look.
be your scribe again.
Oh, I didn't go over those statements. There's a lot of ways that we can phrase an implication, and an implication is oftentimes hidden in a statement without us realizing what exactly the implication is saying. So let's go over some examples. Maybe the author just has them for me so I can just read them to you. Do. You know the song too?
You know the song, dude. It's Night Blue.
Implies, yes, yes. Alright, is the reasoning in exercises 8 through 18 correct? So let's go through if the reasoning is correct. This is using implications. So in other words, does the premise imply the conclusion? Just like if x equals 2, then 2x equals 4. Oh, this is before it even comes up with the truth table. Yes, we can still go over it. So, premises. All men are mortal, Socrates is a man. Conclusion, Socrates is mortal. True or false?
True.
Not true or false, good logic or bad logic. Happens to be true, but it's also good logic, right? Here's where we're checking the logic rather than the truth or falsity of it. So valid or invalid is where we're asking.
Well,
Okay.
the premise was that all men are mortal.
All men are mortal,
So
Socrates is a man.
It's the same thing as saying, if all men are mortal, then Socrates is a man. It's an implication.
If all men are mortal and if Socrates is a
Yeah,
man,
sorry, that's what I meant.
then Socrates
Socrates
is
is
mortal.
mortal.
Yes, right. So, all widgets are gadgets. This is a gadget. Conclusion. This is a widget.
Yes.
Always
Good
guidance.
All widgets are gadgets. This is a
No,
gadget.
No.
Conclusion. This is a widget.
No, because
Not
not all
logic.
gadgets
Oh yeah,
are
no, all
widgets.
gadgets.
So bad logic.
So all widgets are gadgets. That doesn't mean all gadgets are widgets.
Right.
So all widgets are gadgets. This is a gadget. Conclusion. This is a widget. No.
Bad logic.
Bad logic.
The writer to this book. Fine.
Next.
Did you see some of those questions? There's so
Same
many.
thing as Greek math, right?
All-
Stuff like that.
All widgets are gadgets. This is a gadget. Conclusion. This is a widget. Can we do that?
Yeah.
You just switched the
I
widget to
thought
gadget.
something
so
weird
it's
was
15.
gonna be.
Next one. All widgets are gadgets. This is a widget.
Conclusion.
This is a gadget?
Yes, that's true.
That one works. All widgets are gadgets. This is a widget. Therefore, this is a gadget.
I wish widget gadgets were real things.
Every equilateral triangle is isosceles. Triangle ABC is isosceles. Therefore, triangle ABC is equilateral.
Bad logic.
Bad. Parallel lines do not intersect. Lines R and S intersect. Conclusion. Lines R and S are not parallel.
Good logic. Good logic.
Yeah.
We
Okay, enough of those.
use everyday sentences, we get confused, but when you use math and
Yeah,
geometry.
you're very used to the math sentences. So it comes up with the truth table, shows you that an implication is the same thing as not A or B. And then he moves on to the converse without it. Really? He doesn't get them? Fine, I'll come up with them. Okay, so oftentimes when you're looking at a sentence, it's hard to identify the implication hidden in the sentence. So let's go over a couple. Donnie, maybe I'll just say them out loud instead of having to write, and then you can tell me them. Donnie's playing football if Donnie's wearing shoes. So Donnie's playing football if Donnie's wearing shoes. What's the implication in there?
If Donnie's wearing shoes, then
Right, so that's if beta, then maybe I'll just write it to the side over here. This is saying beta implies alpha. It's saying if beta is true, then alpha is true. So let's do that one more time to make sure it clicks with the words. Donnie's playing football if Donnie's wearing shoes means if Donnie's wearing shoes, then Donnie's playing football.
he has those examples in the homework, I'm pretty sure. Like I remember going over it a
I
ton
think
of
it's
them.
just later.
Yeah, it's probably just later, but want to cover it with implications before we move on to logical equivalent. Logically equivalent because we need to do if and only if. So now let's, well, we could just do the other one, that's the confusing one. Alpha only if beta. So what was alpha?
Donnie's playing football.
Donnie's playing football if Donnie's wearing shoes meant Donnie's wearing shoes implies Donnie's playing football.
Yeah.
Donnie's wearing shoes only if Donnie's playing football means
No.
No.
I did that right.
Donnie's
Donnie's
playing
playing football only if
Donnie's
Donnie's wearing shoes.
Donnie's playing football only if Donnie's wearing shoes means what?
Means if Donnie's not wearing shoes, then Donnie's not playing football.
No. It means B implies.
I'd have to think about that one. You said,
Not.
I lost track of which one's which. Donnie's playing football if only if Donnie's wearing shoes, and you said
If Donnie's not wearing shoes, then Donnie's not playing football.
you said that not beta implies not alpha, which actually works.
Yeah.
Because that's logically equivalent with alpha implies beta. Interesting that that's what works for you. So if you do the truth table for this and this, you get the exact same thing. That's interesting how that works for you. Okay. Does that same thinking work for everyone else in here? Or is this still weird?
Alpha implies
Go over it one more time.
Here, let's try one that makes
This one made pretty good sense.
That's the one you used for last time. Same example you used for us.
Football?
let's do Donnie's hungry if Donnie's at a restaurant. Okay? Donnie's hungry if Donnie's at a restaurant means
Donnie's at a restaurant, he's hungry.
Donnie's at a restaurant implies Donnie's hungry.
Mm-hmm.
Right.
Now let's look at this one. Donnie's hungry only if he's at a restaurant. Did I say that right? How did I say it up here?
You said.
So the only reason.
Donnie's at a restaurant if Donnie's hungry.
What?
No.
It was the other way around.
Oh, do I keep switching it?
Donnie's hungry if.
Let's do it that way.
You said Donnie's hungry.
Let's just write the statement down. Donnie's at a restaurant.
That's
Donnie's
beta.
hungry.
No.
That's beta.
That's an
Donnie's hungry
implication.
if he's at a restaurant.
Donnie's at a restaurant.
Then he's hungry.
That would be an implication.
Alpha was Donnie is
If
hungry.
he is hungry.
Yeah, Donnie is hungry
If he's at a restaurant.
That's what you said.
Donnie's at a restaurant if he's hungry.
That's
There we
the
go.
Converse.
Doesn't matter which one we do. Let's just write one down so that we don't switch as we go.
Okay.
So Donnie's at a restaurant if
He's hungry.
Donnie's hungry.
No, he never gets hungry outside of being hungry.
And let's write the other one. Donnie's
Only if
at a restaurant only if Donnie's hungry. And let's make sure that we get the difference in these two statements. Okay, so Donnie's at a restaurant if Donnie's hungry. Meaning, my being hungry is a reason I could be at a restaurant. Why are you at a restaurant? Because I was hungry is the valid answer.
Means that
It could also be I want to check out their menu. Is it possible in this scenario that I go to a restaurant just to check out their menu?
Yes.
That's possible. We just know if I'm hungry, I'm at a restaurant. My being hungry implies I'm at a restaurant, but I could be at a restaurant for other reasons.
yeah, it's true.
Donnie's at a restaurant only if he's hungry means the only circumstance under which I'm at a restaurant is
Because you're hungry.
I'm hungry. So this one is saying anytime I'm at a restaurant, I'm hungry. This one's saying anytime I'm hungry, then I'm at a restaurant.
Right.
Is that clicking? How this one's saying this implies this, but this one's saying this implies this.
Yeah.
So when you have alpha implies beta, when you have alpha if beta, that beta implies alpha. And when you have alpha only if beta, That's alpha implies beta.
Right.
Did that click for everyone?
Yeah.
And then there's other ways that you could dress up the sentence, like alpha implies beta is the same as which of these?
The bottom one.
The bottom one, right? Alpha is a sufficient condition for beta.
Is a sufficient condition. So
Mhm.
that's the second one.
That's the bottom one.
What's a sufficient condition?
If you know, it's sufficient to know alpha to conclude beta.
Same thing as an implication.
Yep. The other one is a necessary condition.
Okay.
If I say alpha is a necessary condition of beta, that's the top one.
Bottom.
Top. It's necessary that this is true, if this is true.
If Donnie is hungry, then it is necessary he's at a restaurant. What I'm saying is, every time Donnie's hungry.
It's sufficient to know I'm hungry,
If you're
to
at
know I'm at a restaurant.
Okay.
It's necessary I'm at a restaurant if you know I'm hungry.
Yeah.
So if I have alpha concludes beta, you know beta's true from alpha,
Being true.
from alpha being true. So alpha is a sufficient condition of beta, but beta is just a necessary condition of alpha.
Okay.
So if I know the truth of this, I for sure know the truth of this. How can I say that the other way without confusing you?
Well,
If you have alpha implies beta, this we call the necessary, this we call a sufficient condition, this we call the necessary condition.
Right.
This is necessarily true if this is true. This is, maybe that's not the right way to say it.
Well, if Donnie's hungry, it is necessary he's at a restaurant.
Right, if that statement's true, then it's necessary I'm at a restaurant. But just because you know I'm at a restaurant doesn't mean I'm hungry.
Right.
Right. Good. Okay, so those were the weird cases with implication. Now we'll move on with what the book says. Is that still going?
Yes.
Didn't die? I hope my charger's still working. Okay, so now we're ready to talk about the converse of an implication. The converse of an implication is straightforward, it's just flat out flipping it. Converse. Converse of alpha implies beta is beta implies alpha. So, if I'm wearing shoes, then I'm playing football. What's the converse of that?
If you're playing football, then you're wearing shoes.
And you get how they'll say two very different things,
Yeah.
right? Okay.
What's a converse? That's not the contradiction.
No, the converse is exactly that.
Well, what?
This is a converse of this.
Okay,
It's
well-
the first time we introduced the word.
Okay. I was wondering if there were converses of
We talked about contradiction and we talked about
contrary.
contrary. Thank you. All right, give me the converse. If an animal is a man, then it is a human being.
An animal is a human being, then it is a man.
Good. You see how
Yeah.
those are very different? We don't need more examples of those. So now we're ready for equivalent statements. So this is the last operator that we're going to talk about. So we've talked about and or not implication. And the last one we're going to talk about is equivalent.
And converse.
Huh?
It says and converse.
It's just another word, but it's the same logical operator. We didn't introduce a new operator for it. Makes sense what I'm saying? Okay, so the next operator we're going to introduce is equivalent, and that's an arrow back and forth. And the arrow back and forth, equivalence, like that, we define it in terms of, maybe I'll say it this way. Alpha is logically equivalent to beta, this means the exact same thing as alpha implies beta, and beta implies alpha. Good with that? The way that we say this in English is we say alpha if and only if beta. And see how that's the same as over here. This is one way that we can say alpha implies beta is.
Alpha only if beta.
Yeah, I should have done these in a different order, huh?
Why?
Well, the beta implies alpha just to make it match it better with how I read it. I'm going to write the exact same thing, I just changed the order. Beta implies alpha, and alpha implies beta. Why do I keep switching? Okay, so alpha is logically equivalent to beta, means beta implies alpha and alpha implies beta. Good. So, the way we read this is alpha if and only if beta. The way that we could read this is beta implies alpha could be alpha. Why do I keep doing that? Alpha if beta, right? And for our and, so alpha if beta and alpha implies beta is the same thing as
Beta
alpha
and
only if beta.
Okay.
Yeah.
And that's why we say if and only if over here. So alpha if and only if beta is a shorthand for combining these two sentences. Alpha if beta and alpha only if beta.
That would make sense.
So this is a shorthand for this, and we do this so much we even have a shorthand for this. And we do alpha if beta with two F's. So when you see the double F if, that means if and only if. Good? And so that's how so I might write this on the board, but when I read this every time I'll say alpha if and only if beta. Any sense?
If
That
and
shorthand
only
for
if
that,
does
shorthand for
not,
that.
if and only if does not make sense in a sentence.
Yeah, it does.
Yeah.
Like,
What I'm saying is I understand if and only if has always been a short-term way to write that.
Well, it still logically makes sense to us.
No, it doesn't. If and only if.
Uh-huh.
Explain it to me.
Okay. 2x equals 4 if and only if x equals 2.
Okay, 2x equals 4 if x equals 2. Well, I'm saying
Yes,
you
but
didn't
that's-
need
but-
if and only if.
But also the converse.
So, when I say 2x equals 4 if and only if x equals 2, means that those are logically equivalent. It means if 2x equals 4, then x equals 2, and if x equals 2, then 2x equals 4.
Okay.
Make sense?
Yes, but if and only if does not.
This is a scenario and the only scenario. Alpha is true in this and only this scenario for beta.
Okay.
It's not
2x equals 4 if and only if x equals 2. There's no other scenario you can find
Right.
other than that one. Those two, the way I think about it is those two would tell the same information. They're logically equivalent. So let's write out the logic table for this, finally. The truth table, sorry. So truth table. So we're going to have alpha, we're going to have beta, and then we're going to have, we don't need parentheses yet. We'll write alpha implies beta. We'll write beta implies alpha. And then we'll write alpha implies beta and beta implies alpha. You understand what we're going to do?
Yeah.
We're going to look at what the truth table looks like for if and only if. So our possible combinations are, well, let's fill it out. Right? Those are all the possible combinations. Okay? Well, I'll just say it this way. True implies true is.
True.
True implies false is.
False.
False implies true is.
True.
False implies false is.
True.
Next one. True implies true is.
True.
False implies true is.
True.
True.
Yes.
Alright. True implies false is.
False.
False implies false is.
True.
True.
Okay. So here's alpha implies beta, here's beta implies alpha. Now we're going to and them together.
So
Good.
True, false, false, true.
So true, false, false, true. Good?
These patterns are weird.
Now here's what you notice. Alpha implies beta, beta implies alpha is true only when alpha and beta have the same value.
Right.
That's what it means. So now write this. True, false, false, true. We say that these are logically equivalent if they have the same truth value.
Right.
They're not logically equivalent if they have different values. So true, false, false, true. Good? Okay, and that is equivalence. So we did that. Let's see, reasoning for the exercises. For statements equivalent to those listed below. Oh, form statements equivalent to those listed below. If you're not sure of the equivalence, make a truth table and check the work. I want you to make up statements equivalent to. Not like that.
I understand the not. So.
We'll just continue and then we'll look at the exercises at the end of the chapter. Say that again.
Body is not holding a blue marker if and only if he's not holding a red. True.
Depends on the scenario.
Yeah.
Well, what I'm saying is, if they're both false.
So I'm not holding anything. Donnie's holding a blue marker if and only if he's holding a red. True.
True.
But if you're holding a red, you'd be screwed. Well,
Donnie's holding a blue marker if and only if he's holding a red.
false.
False.
Okay, that does make sense.
Okay. Contrapositive of implication. So, just erase to here. Here's our implication for alpha implies beta. And now we're going to look at the contrapositive and show it's logically equivalent. So the contrapositive of alpha implies beta, I'm done writing out all the definitions, we'll just figure it out and apply. Alpha implies beta, the contrapositive of that is not beta implies not alpha. And these two things are logically equivalent. And sometimes it's easier to think about a proof, an implication this way versus this way. There's tons of times where it's useful. But let's just see an example of it real quick. We'll use a valid statement so that we don't hurt our brains. So here we could have something like, if x equals 2, then 2x equals 4 is logically equivalent to if 2x is not equal to 4, then x is not equal to 2.
Yeah.
Right? If this is true, then this is true is logically equivalent to if this is not true, then this is not true. Then, is that why you were laughing?
Yes.
I wondered why. Okay, so we're going to prove that this is called the contrapositive of this. We're going to prove that the contrapositive is logically equivalent. How do we prove that? Just a nice, easy truth table. So let's. We've got we've got alpha, beta. We've got alpha implies beta. We need to write not alpha, not beta, and then not beta implies not alpha. So maybe it'll be easier to write not beta first, then do not alpha, then do not beta implies not alpha. Okay, so let's write it out.
False. True.
True.
False. True. False. False.
True.
False implies false is.
True.
True.
True implies false is.
False.
False. False implies true is.
True.
True implies true is.
True.
So true, false, true, true. True, false, true, true. Yep, they have the exact same values no matter what scenario you're talking about. Therefore, they are logically equivalent.
Put in your.
There are two ways of saying the exact same thing. And the other way, in fact, the way that this author introduces the definition of implication is he introduces it as not alpha or beta. And I don't like defining implication that way. I like to just think about it and come up with it. But that's the way this author does it, so let's see, this is also logically equivalent.
Okay.
So we're ORing not alpha and beta. We're ORing these two together. So true and false is
True or false.
Right.
true or false
True.
is true. False or false is
False.
Wait, it's not A, Donnie. Oh, sorry. Yeah, you're pointing at it.
true or true is
True.
false or true is.
True.
So true, false, true, 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 false, true, 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 false, true, true. So this is 3 different ways of writing the exact same thing. So if Donnie's holding a blue marker, then Donnie's holding a red marker, says the exact same thing as if Donnie's not holding a red marker, then Donnie's not holding a blue marker, says the exact same thing as Donnie's not holding a blue marker or Donnie's holding a red marker.
Which makes sense.
Those all say the exact same thing. There's no logical difference between any of those. So there's a bunch of different ways that you can formulate an implication, and sometimes one of them appeals to your intuition, appeals to your brain better than other ways of it. So sometimes knowing these little substitutions you can do is real useful for the proofs you have to do. So that is contrapositive. If and only if we did that. Theorems and proofs.
We're not getting into theorems.
We're not going to get to theorems and proofs in our, well, we will do proofs. I'm not sure exactly how this whole logic book's going to flow and what we're going to use and not going to use, but maybe I'll talk about, just for general education if it doesn't end up being useful later, the way a system of math works in general. So the way a system of math works in general is there's 4 components to it. First off, there's what we call undefined terms. You can't define every word that you're going to use. What's the problem with that?
It's not consistent.
Either you're going to have infinite language, or somewhere along the way you're going to have circular definitions. Right? So you have to have what are called undefined terms. You have to have what are called definitions. You all understand what a definition is.
Yeah.
You have to have what are called axioms, which are basic assumptions that you operate on. And then you have your theorems. So if we're talking about Euclid's elements, and if you open Euclid's elements, he gives you a bunch of definitions, and then he only makes 10 assumptions. So he makes 10 assumptions. He said, this is true, this is true, this is true, 3, 4, 5, whatever, and 5 more. And then all the rest of his books are determining the logical implications of these statements. So since this statement's true and this statement's true, together they make this statement true. So this together with this implies this statement. Oh, okay. And then he says, well, now I know that this is true with this statement and this, I'm able to come up with this statement is also true. And he starts building out this massive web of what we call theorems. Maybe this one also relied on that fact. From there on out. So you start with definitions and undefined terms and then these premises. And then from there on out, you're seeing what are the logical implications of those premises. And those are called theorems. Make sense?
Yeah.
So that's what a theorem is. It's a logical implication. And so, maybe seeing this in action will be best when we do the algebra examples at the end. So theorems and proofs. So yeah, so that's the end of the chapter. Let's just jump into the algebra review because I think you guys are most comfortable with algebra and it will help you see some of the premises, what we were talking about. So we're going to solve some algebra problems and you're only going to be able to use exactly what I give you here. So, in the exercises below, we indicate some of the ways that logical reasoning is used in algebra. First, we shall list some statements that we agree to call true in algebra. Then we shall set up algebraic problems which provide opportunities to use true statements and reason logically to correct conclusions. In what follows, all letters refer to integers, that is, whole numbers. Everyone understand what an integer is? Positive or negative whole number, including 0.
Yeah.
Okay. So we're going to make 2 assumptions, and then we're going to do proofs using these assumptions. So one of the assumptions we're going to make, I'm just going to hold it right. So one of our assumptions, assumption 1, for all integers A, B, C, it is true that, please keep listening, it's true that if A plus B is equal to A plus C, then B equals C. 2. For all integers, A, B,
What
C.
I'm wondering is, according to Euclid's,
No. No, I guess we could have done that if we wanted to, but
I really enjoyed it.
it is true that if AB is equal to AC and A is not equal to 0, then B is equal to C. You understand those 2 assumptions?
well, integers A, C is true that. Yes.
Okay, so now let's do a proof like we would in any class. So we're going to prove if x is equal to 5, then 3x plus 4 is equal to 19.
Okay, let's do this.
Okay? So, since we know x is equal to 5, I don't know how much we want to write out. Since x is equal to 5, then 3x plus 4 equal to 19. Should I just do my arrow? Pretty sure that's what he's going to do.
Implies. You can't use substitution, Donnie.
Oh, what am I doing? Sorry. I'm looking at 2 things at the same time, wondering what's wrong with it. Okay, since x equals 5, then 3x plus 4 is equal to 3 times 5 plus 4 is equal to 19.
Yeah.
Good?
Yeah.
That one's nice and straightforward. Then we'll do a more interesting one. So now let's prove the converse of that. And this is
You
where it's
didn't
more
use
interesting.
any of your 1 and 2.
I
did.
No, you did
No,
not.
I didn't have to for that.
He substituted his exit.
So now, let's do the converse of this, and this is where it gets more interesting. So I'm going to prove, now I'm going to do if 3x plus 4 equals 19, then x equals 5. Good?
Yeah.
So, since 3x plus 4 equals 19, that gives us,
Okay, wait. Let's see if we can do this.
well, I'm probably going to use it, I don't know if the author uses this trick.
Probably separate your 19 into an addition.
Right. So that gives us 3x plus 4 is equal to, what's another way to write 19?
15 plus 4.
15 plus 4.
Is equal to 3 times 5 plus 4.
Which gives us 3x plus 4 is equal to, another way to write 15 is 3 times 5. Which gives us, now we'll use 1.
2.
Well,
1, which gives me 3x is equal to 3 times 5.
right.
Oh.
Now this is using 1, and now this is using 2. And we proved it. We're done.
Wait, 1 sec. How did he use 1 on that?
Because you have to figure this first.
To get rid of the force.
You just said, oh look, they're equal, cancel.
Look, this says if something
Oh,
plus
right.
b is equal to the same thing plus c,
Right.
means you're equal.
Right.
Is that just a,
Oh, I guess I need to use associativity, huh?
why?
I was gonna say, aren't there other rules that you're applying that you don't necessarily?
Yeah, so we're implying that you already know how to add and that you can multiply.
Yeah.
Yeah, so that's the same comment I made when we first came across these is, I don't like that the author isn't explicitly stating everything you can use. He's just telling you some of the things you can use. But in short, what he's saying is, you don't get a subtract from both sides and you don't get a divide both sides by the same number, is what he's forcing you to not be able to do. And he's forcing you to use these rules instead.
Right.
That's
Which
what
we did. We did everything legitimate.
Alright, so let's try another one now. So I'll get rid of that work. And let's do prove if 4x plus 5 equals 33, then x equals 7.
It's not you.
Alright, who's doing it?
This is the
It's gonna
same
be the same
exact
thing we
proof.
just did.
So then do it.
Well, you want me to prove that?
No, I specifically negated the
Yeah.
first way because there was no point in that.
Do I have to write if and stuff? Can I just do it algebraically? Help me out, Levi. Equals 28 plus 5.
So he rewrote 33 as 28 plus 5.
Then that equals.
Using number 1.
Yeah, then using 1, you can write that as. Oh, never mind. He's going to do what I did to
Oh yeah, yes.
write it all out. He didn't have to, and he
Good.
doesn't know how to multiply. Somebody help him with that.
Then using number 1. Using number 1 in this one. 4x equals 7 times 4. And using number 2, x equals 7.
The only reason you fell right there is because you didn't use English.
Alright, who's next up there? And I'll read the prompt to you.
I'll do it.
I've done stand-in, so from here on out, you guys are up there.
See if I cannot make a fool of myself doing this.
Alright, it says, prove that 5x plus negative 3 equals 27, and it has negative 3 in parentheses, equals 27, only if x equals 6.
Okay. And I use these two rules.
Yeah, you can use those two rules, but you're showing which one implies which one?
The first and
6
the second.
implies the second. So you'll just plug
No.
it in, Levi.
No, you're implying that the
5x plus negative 3.
If
implies
x equals 6.
x equals 6.
X equals 6.
So what does he start with?
You start with
Start
x
the
equals 6.
equation.
Start with x equals 6.
Right? Yeah, because that's where the if is. So
Right.
if x equals 6, then 5x plus negative 3 equals 27? No!
Yeah.
Yeah.
Only if.
Start with
No.
negation.
Only
I
if.
don't start with this, do I?
Only if.
Yes,
Right,
you do.
start with
No.
negation.
Only
implies beta.
Not if, only if. Alpha only if beta.
So
Not alpha if
implies
beta.
Okay, look. Alpha only if beta means the exact same thing as beta
Doesn't.
implies alpha.
Should have
No.
left these up there because I knew
Yes.
that this would happen.
We should have.
So alpha if beta means
Beta
beta
implies
implies
alpha.
alpha.
Uh-huh.
Right.
Alpha only if beta.
Means alpha implies beta.
Oh yeah,
Alpha
you're
implies
right.
beta.
I know I'm right.
Oh, yeah.
Okay.
Told you. All right, Leah, you just volunteered for the next one.
You're ready for the next one.
beta. 27. 24 minus
Oh,
negative
sorry,
3.
3. It's supposed to be 3.
5x plus negative 3 equals 27 implies 5x plus
Oh.
negative 3 equals 30 plus negative 3. Good.
Good job. And just because I didn't do arrows doesn't mean you're better than
Okay.
These scribbles and boxes.
Oh my god, I knew that was gonna happen.
All right, someone else get up there.
Where I agree with this Leo.
Stop being chickens. Everyone's going. May as well get it out of the way. We only get harder.
Yeah, you're gonna be
I should have
going.
waited until the end. It's way more fun to do hard.
You ready for it?
No.
How about now?
Yep.
All right. Prove that x equals 11 is a necessary condition.
How do you spell necessary?
Necessary.
1 C, 2 S's.
Necessary, that's a good
Whoa.
Forgot.
Close enough.
One
Condition.
C, 2 S's, right?
Yeah.
Necessary. N-E-C-E. C-E. Necessary. Ness. E. S-S-A-R.
Necessary.
Yeah. Okay. Condition. For 5x plus 4 equals 59. 5x plus 4 equals 59.
59.
Mm-hmm. All right, so alpha is a necessary condition for beta, means
Beta implies alpha.
Alpha implies beta.
Alpha implies
Beta
beta.
implies alpha. If X,
Leah, tell him.
I think it's alpha implies beta.
what's this?
No,
what's
it's
the-
beta implies alpha. Beta is a necessary condition for alpha. Alpha is a sufficient condition for beta.
Sufficient.
So when you have alpha implies beta, alpha is a sufficient, beta is a necessary.
Well, I just think necessary is after if.
What?
Right?
What?
So it's gonna be, you have to start with
It's
5x.
gonna be with the equation, yes.
Yeah, you're trying with 5x plus 4 equals 59.
Because beta implies alpha. I just screwed up. I think if x equals 11 is a necessary condition.
I'm bad at
Ooh, the next one's gonna be brutal.
Huh?
And it only gets harder.
Should have waited.
Yeah, all the little girls are holding out.
Yeah.
My line of vision's cut off. Don't feel bad.
Then using 1.
So let's see what he has. 5x plus 4 equals 59 implies 55 plus 4. Is 55 plus 4 a statement?
Equals something.
Oh. Right?
Yeah.
Sure.
And then using roll 1.
I don't know what you have written underneath there. Oh, 5x equals 55 using row 1. Okay.
Okay. And then, which implies 5x equals times 11,
Mm-hmm.
which also implies using roll 2. X equals 11.
There we are. Okay, who's
Part of
next?
that proof was necessary.
This is all the same concept to it. It's just different ways of writing the same concept.
Well, it's just trying to figure out what implies what. But their trick is.
So the trick is just deciphering the first part. That's
Yeah,
all we're doing.
but the first
Okay.
one's always the same. Just give me the equation.
Prove that 2x plus 7 equals 19. If and only if four x minus 3 equals 21.
Oh, I see why you said it was harder, because you have to go both ways now.
Well, you just have to make.
Well,
one
and you're
look
also
like
not
the
just
other.
getting to a number.
You just make one look like the other. That's all you have to do.
Well, the point is you have to prove if, and then you have to prove only if.
Oh, you have to make one look like the other, and then make the other
Yeah,
look like the one.
yeah.
Okay, that makes sense.
So
So start
you're gonna
with
have
your
to,
2x.
you're gonna have to start alpha implies beta, and then after that you have to prove beta implies alpha.
Right.
Well, she knows that she needs to show that if 2x plus 7 equals 19, then 4x minus 3 equals 21. But then where do you go from here?
What?
I don't even know what I
Look,
You know what you're doing? You're showing that if this is true, then this is true, right?
Okay.
Think about how you just do this naturally. What would you naturally do? You'd look at this and you say, okay, since 2x plus 7 equals 19, then what?
Minus 7 equals
Don't worry about proving anything, just what does your brain say? What do you now know?
2x equals 12.
If I tell you that 2x plus 7 equals 19, then what do you know?
2x plus 7 equals.
But you would know how to say, if I said
X equals
solve
6.
this, what would you do?
Oh yeah.
What would you do?
It'd be x equals 6.
You get x equals 6. Then is this true?
No.
It's not. What's 4 times 6?
Oh, yeah it is.
So if this is true, then this is true.
Okay.
And if this is true, then this is true.
So you have to prove both ways.
Okay.
Does that make sense?
Yeah.
So it now makes sense to your brain that if this is true, then this is true, and if this is true, then this is true. Now you need to prove it. So in short, what you're going to do,
So you're going to.
let's see what you got.
Okay. Okay. So first we're going to start out with the equation. This equation implies that seven equals 12 plus 7. And then using number 1, you can get that 2x equals
Okay, fine.
If we're going this way, then we go this way, then we go this way.
and then you
do it.
This implies that.
So now
Now
you
she has to work backwards to get the equation.
right. So now just take your 4x.
Let's
So
think
now you
it through. Remember where you're trying to get. You're trying to show that since this is true, this is true. You know that since this is true, this is true. But you're trying to show that since this is true, this is true.
This is true.
Sure. So how do you continue?
Because if that's
You
true,
So
what
then-
she's trying to do is
well, substitute
Multiple
both
sides.
away from each one.
to show that it's the same.
Let me put it in words. I'm saying to you, prove that 4x minus 3 equals 21
Well,
if 2x plus 7 equals 19.
I make them both equal 6.
Well, that's
Now you just showed that this and means this.
Right.
she's
So
just
another way I can
showing
say that
all
is
places.
prove that 4x minus 3 equals 21 if x equals 6.
If x equals 6.
Yeah. How would you do that?
He's just gonna substitute it. Like just,
Well,
he's just gonna
if
say,
you're trying to use these two properties, that's the reason they're
You
out
can't
So
just
you-
substitute it in,
Why not?
can you?
Yeah.
see,
there. You could simplify it, but why do that when you?
Well-
So
Can
x
use your
equals
rules,
6, so 4x minus 3 is 4 6 minus 3.
Okay.
X is 6. Yeah, you're not
This
cheating
one
when you do
was-
that.
that's true, right?
You can substitute it, but isn't kind of what the author's trying to make you do is use the two rules.
Yeah.
Those two rules are basically
Right.
saying, here's what you're not allowed to do. You're not allowed to subtract from both sides, and you're not allowed to divide both sides by
So
something.
you can't substitute.
No, you can definitely substitute. Substituting is actually a rule of logic. It's not even a rule of math.
Right.
It's identity. You're saying x is 6. You're saying that those are encoding the exact same thing. So yeah, you
Yeah,
can
that's
swap those
what
out.
he did is illegal. No, you can't do that, Leah.
She probably can.
Oh yeah, yes you can actually.
That's gonna be for
Austin, you ready to look at some logic?
She's already forbidden.
Is she in that developmental stage yet?
Nah, she's got 2 or 3 years.
that. 2 or
Secretly, he wanted us to keep it.
Oops, what did I do?
You were manipulating both sides of the equation when you were just trying to
Oh,
show
yeah,
that
that's true.
this is equal to this.
Oops.
So you know that this,
Oh, I did it right. That's equal.
well, here's what I would have done. You're on the right track, just to make the thinking clear. I now come down and say, so now 4x minus 3 is equal to 4 6 minus 3 is equal to 24 minus 3 is equal to 21.
Okay.
You see what I'm saying?
Yeah.
Because now you show this equals this, which is what you're trying to do. You're trying to show since this is true, this equals this. Make sense?
Yeah.
So that was one direction. All right, we'll have someone else do the other direction.
Well, obviously.
Times
think-
dynamic.
Yep. Okay, so now you're proving if this is true, then this is true. So you're starting with this and you're trying to get to here.
Okay, and I can't do the exact same thing that Leah did.
You can do really close to the exact same thing she did.
You're just
Yeah,
going
exact
backwards.
same.
You're just going to start with this one.
It's just the difference.
So you know that 4x minus 3 equals 21.
Yeah.
So then what do you know about x?
That it's 6.
How?
Just cause.
That's a natural way to want to go, but now you need to use your rules. So you have 4x is equal, I write 4x plus negative 3 to help you see how it's applying. Put parentheses around that. Is equal to 21. Now you're trying to simplify so you get x equals a number, right?
Yeah.
So you need to get rid of this negative 3, you need to get rid of the 4.
Right.
So you need to use rule 1 to get rid of the negative 3, and then you're going to use rule 2 to get rid of the 4.
Okay.
So you need to rewrite 21 so that something plus negative 3.
So it needs to be, so you're saying 4x plus negative 3 equals 24
So now you can use rule 1 to cancel out the negative 3's.
Equals 24. And then rule 2 is 4.
Like that background. That background looks
Right.
like God.
So you can rewrite 24 as 4 times 6, and then using rule 2, you can write x equals 6. Okay, so now you have x equals 6, but remember where you're going. You were saying if this is true, then this is true.
Right.
So you found out if this is true, then x equals 6. Now you need to use that information to prove that 2x plus 7 equals 19.
So, and I can just substitute because that's the only way to go.
Yeah, because you just found out x equals 6, so now 2x plus 7.
Do x?
Yeah, so I'll start out with 2x plus 7 is now equal to what? Do your substitution.
Is now equal to 12
Sure. Plus 7,
plus 7,
which is equal to.
19.
Which is what you're trying to prove. So you're showing if this is true, then 2x plus 7 equals 19. So since this was true, x equals 6, and since x equals 6, 2x plus 7 equals 19.
Right.
Alright.
Is that it?
Yep. Who's doing the next one?
The prime.
She got it when I said it. Alright.
If and only if statements.
Prove that there is no number x.
You'll do 12 lines for the first
Is
sentence.
there a way to write that?
12 lines for the second.
Like, you want me to write the whole sentence?
All changes.
Yeah, that way everyone can read
Strike
it.
them and
Remember, you're not just doing it for you.
Then you bring it to class. No.
Prove that there is no number x such that 3x plus 5 equals 11 and 4x minus 1 equals 3.
They're just adding on knots and changing, it's basically just changing the way it's at.
Well, kind of. Now, this is a much different
Way
one.
different.
Prove that there is no number x
There's not an X.
such that
3X.
3x plus 5 equals 11 and 4x minus 1 equals 3.
So, you could prove it by contradiction, like that'd be the easiest way to go, wouldn't it?
Yeah, it's going to have to lead to a contradiction.
Well, you could say assume.
But you're
there
not
is
going
an
to do
X.
a proof by contradiction. You're going to show that
That x is
no matter what,
You would-
this is false.
You would show that x equals one number and x equals a different number, and that can't be true.
Kind of.
Isn't this the same thing as, and then just put in parentheses that?
Show that there is no x such that
Like the
3x plus 5 equals 11 and 4x minus 1 equals 3. Let's think. There is no x. Kind of. That would be the negation of for all x. 3x plus 5. No. That would be the negation of there is an x. There exists an x such that 3x plus 5 equals 11 and 4x minus 1 equals 3. So that's what it's a negation of.
Right.
So it would be not,
So we're trying to prove
there exists x
that is
such that
false.
3x plus
Both
5 equals
those
11 and
x's
4x
solve
minus 1
each
equals 3.
equation is true.
So I'm right to think that.
Well, what we're saying
If
is
you're
no-
going to write in there what I think,
I'm
you
just-
can't just write this is what I'm saying.
The same x.
Right. Yes.
That's not quite logically what it's saying. If you want logically right now, you're saying
We're
not
gonna get 2 on that one. and
there
then we're gonna
exists
get
x
1 on that.
such that.
Or, you know what I'm saying.
Yes.
Oh,
You see what I'm saying?
You
Okay.
can't.
You still have
There's
that
not
x
a number you can plug in both
quantifier,
those equations in.
which is
in
going to
conjugation.
hurt you. So I'm thinking the way that you want to do this is
You
show
have to reach in the stars there.
if this is true, this is
You'll
false.
see, it's
And if
actually
this
cool.
is true, this is false.
You'll prove it using these two.
Therefore, this and this is false.
alright.
You see what I'm saying?
Mhm.
I think that that's the best way to do it. Maybe, I don't know if someone has a better idea. Because the only way that alpha and beta can be true is if alpha is true and beta is false. Or is if alpha is true and beta is true, right? So if alpha being true implies beta is false, and if beta being true implies alpha is false, then you can't ever have alpha and beta true.
Mm-hmm.
Alright.
Like, do we need to whip up a quick truth table
Yes,
to see this?
please.
It's just another form of an if and only if, basically.
So if I know that alpha implies beta is false, and if I know that beta implies alpha is false, okay? So let's write up our truth table for all the possibilities. So we have alpha, beta, alpha implies beta, beta implies alpha, and then we'll do alpha and beta. True, true, false, false, true, false, true, false. So alpha implies beta, true, false, true, true. Beta implies alpha, true, true. I'm looking at the wrong one. False, true. And then alpha and beta is true, false, 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 right? So if I know alpha implies beta is false, that means alpha implies beta is false.
Right.
So alpha and beta can't be true in that scenario.
Right.
That's all we have to show actually, and we're done.
Right. That's,
So you can just
that
use
is
the
what I was.
So we don't need to show
So
both of
that's,
them.
that's
Just-
way faster.
If
show
you
that.
just show alpha implies beta, then this has to be
That's the trick, though. How do you show that alpha
Maybe that's
does not
not
imply beta? Or sorry.
showing alpha implies beta is false.
You show that if you get to X,
Can't you
then you
just-
can't go the other way to get
Right, isn't, that makes sense.
Is enough to show that they can't both be true. Yeah, that's all you have to do. If
That's
alpha
way
implies
faster than
beta
I
is
was
false, alpha and beta
Then you
cannot
can
be
use
true.
option two.
Alright.
So yeah, that's easier than I thought.
Oh, that is very easy.
Yeah.
Yeah, the trick was recognizing what to do.
I like your studio.
Yeah. Really helps not brighten the place up.
What are the papers for?
So you get a bad glare on the whiteboard
Oh,
from those lights.
I see.
And it's still not great even with those there. It still shows through pretty good. So, but it was way worse before. Alright, so let's see what she's got.
So I've gotten to the point where x equals 2. And
So stupid.
this,
So 3x plus 5 equals 11 implies 3x plus 5 equals 6 plus 5.
Should do is
Use
just
rule
say it's
1.
not equal, therefore.
Rewrite, use rule. Oh, 2. The 2 parentheses threw me off. Okay.
this would imply, oh, sorry. This would imply that that equals, which,
Is not.
it equals 7, which doesn't equal 3.
Oh, that's square up there.
Oh, we can't do exactly.
Well, that shows that alpha implies beta is false, then you can just use the truth table, right?
Isn't that statement not implying?
4x
Right.
minus 1
Right.
equals.
This is, but is
Oh,
this,
equals 7, so it does not equal 3. Okay, yeah, it works. Sorry, what?
but this is
Oh,
an
I should put that
implication.
there.
So how would this?
So what she just really showed is this implies this is not true.
Which is the same thing as
She just really showed alpha implies beta is false. The left-hand side implies right-hand side is false. So if the left-hand side implies right-hand side is false, then it's impossible for both these to be true.
That's what we did with the truth table.
I see.
So there exists no X such that they're true.
So this statement is never true. Doesn't matter the x that you plug in.
Yeah, it's way faster.
Yeah. All right. Here gets the hard one.
Laura.
You said, oh,
Laura. Laura in some TV series. I know I got that from somewhere. Laura. It's the
You got
Canadian
it
way
from-
to say Laura.
I think you got it from Robert.
Laura.
Laura. Right?
Laura.
Robert does say that.
Laura.
That's where I got it
Yanni.
yeah.
Okay.
Yeah, me and Laura.
Okay.
The question is, what can you infer? Here, let's just write this. Skip all that. Just write. A does not equal 0. And A times, in parentheses, 3b minus 8. 3b minus 8 equals A. So, here's what the whole problem says now. What can you infer if it is known that A does not equal 0 and A times 3b, that's a b, not a 6.
3B.
So make sure that that's real clear. 3b minus 8 equals A.
And you
So-
can infer.
What can you infer from that? If you know that A times 3b minus 8 equals A, what does that tell you?
3b minus 8 equals 0.
One.
Yeah, it has to.
But it doesn't make sense if it's one.
Because then
It doesn't make sense if it's 1?
No.
Oh,
if
if
what's
it's
one?
0, it would take
A.
I. 1 makes sense.
Tells you that B.
Well, you can
equals-
use your rules over there. And is there another way that we can rewrite
Tells you A equals
A?
3.
A plus 0.
Yeah, you could do A plus 0, but that's the one you don't want. So what's another way to write A? You probably want to have a times in there, not a plus.
Times 1. Oh, got you.
A times 1, right?
Oh, on that side?
Yeah, so this gives us, so we know that A times 3b minus 8 is equal to A times 1, right?
So you make it equal
No,
one.
no.
Make what equal 1?
Yes.
Yeah.
So, using what?
Well, the first one.
Using this one? So you have something that looks like this? Or do you have something that looks like this?
That.
This, right? So if this tells us if AB equals AC, then B equals C. As long as A isn't 0. Is A 0 over here?
No.
Then we know that B equals C. Calling this whole thing B to follow what we're saying here. Sorry.
Yeah.
There's a-
So
So
that
It was
equals
pretty
that.
crap.
Yeah, so I'll write that.
Legitimate concern.
And that was using rule 2. Okay, now what else do you know?
Oh.
You're gonna want to rewrite.
How do I deal with the 8?
Write it as plus negative 8. Negative 8 equals, now rewrite 1, but with a plus negative 8. There you go.
Ching.
Perfect.
Using rule 2.
That's just great.
Yeah. So you were able to,
Do 1, 2.
you were able to infer that B equals 3 from that statement.
Is that all?
Yeah. That was pretty good. What we were able to do. All right, who's gonna do it next?
I'll do it.
All right, get up there.
I can. If it keeps getting harder, I don't know.
This one's basically the same as the one that she did.
Oh shoot. Should have paid attention.
So, given that r times, in parentheses, 7b minus 5, in parentheses, equals r, what can you prove?
Right.
It's the exact same thing.
That's what I said.
Well, you can
It's like you said the exact same thing I said.
which implies that 7b minus 5 equals r.
One.
Oops, that's what I meant. And then you can
What time is it?
rewrite the one.
What?
9:18.
9:18? So we only have 2 more problems after this and we'll call good?
Saving the best for last, right?
Should probably be writing this out as like a proof, shouldn't it?
Yeah, that would be ideal if you know how to write a proof
But
good.
I mean, it's time consuming. Do you want me to do that?
Just keep going. We can check your work as long as you state which rule you're using.
Oh, this is roll 1.
Okay, so we have.
Up top is roll
You can
one.
keep going. I'm just checking to make sure we didn't make a
Oh,
mistake.
this is roll.
One.
This is roll 2.
Yeah, from here to here is rule 2. And then you rewrote that. Okay, and then. Okay.
And then we'll rewrite this. Wait a
What
minute. I did something wrong.
Is that a -3?
What do you mean you did something
It's
wrong?
supposed to be.
No, that's what you can
That's
imply.
what you can imply.
You can imply 7b equals 6.
That's right, right?
Yeah. 7b equals 6. That's what you can conclude from that.
That's all. Using the integers.
Lane.
Alright, we'll let you prove something cool. Get up there.
Please.
Why did I get the link?
Okay. It is given that 3a plus 12, all in parentheses, times 2b minus 8 in parentheses, equals 0. And b is not equal to 4. What can you be proved?
A is equal to
So-
-4.
So,
Yeah.
we're probably obviously going to want to use number 1 first.
Why? I'd use number 2 first.
Yeah.
Rewrite 0.
0 is the same thing as 0 times 2b minus 8.
That's what I thought. That's what I originally thought. Was. This is what I was thinking, tell me if I'm wrong. Oh, times 1.
What? That's not right.
Why are you wrong?
Because
I
0,
just leave
I have
it as
no
0.
clue what you just did.
that's still 0. There's no
Yeah.
point in timing 1.
You're right.
It's just some weird manners.
That's not talking about it is.
You were on the right track.
You did all right.
You did all
Yeah,
right.
you were.
We just
Okay.
typed by
You were
word.
not wrong.
You're just gonna go back to
Maybe
zero.
he's got another
The
path to
times
go down.
1 was the wrong part.
Okay. So let's pretend I said all that.
You took a number times 0 and you got 1 out of it.
Yeah. Do I need to go back?
We'll let you skip to there. Okay?
No.
Oh, let's
Whoa.
not talk about that either.
Don't erase everything.
You just gotta say 0 is 12 minus 12.
Lucky Levi was here to do your problem for you.
Hey,
Sorry.
I actually
Well,
got that.
minus how big? 12.
He'll figure it out. 0 plus negative 12 is 0. Uh-oh, now you're not going to be able to use that rule.
That worked. That worked.
No, let's slide.
It's getting complicated.
You guys following.
A equals negative 4. Yes, of course.
See, I want you guys to know I didn't do that.
Alright. Only one more problem that has a star next to it, so
Oh,
that
boy.
usually means it's a challenge problem.
I'll do it.
Alright. So it is given that 2a minus 3 in parentheses times b minus 3 in parentheses equals 2a minus 2. Prove that if a equals 1 and b, then b equals 3. Sorry. Prove if a equals 1, then b equals 3.
I'm proving this.
And if a does not equal 1, then b does not equal 3.
Oh, so it's like another if and only if.
And it continues.
Oh.
There's one.
What are the values of a and b if a is not equal to 1?
But that's not part of the proof.
Yeah, so you have two proofs. Those are two separate proofs, not and. So prove this, period. Prove this.
And then prove the
We can continue with the last part after you're done with that.
Okay.
So just start with a equals 1 implies b equals 3.
Alright.
Just substitute A. Oh, okay.
Alright. This implies.
That's kind of skipping a step though, isn't it?
No.
Substitute
I
and
just
simplify.
Substitute and simplify in the same step.
It's called the double S's.
I know, I mean,
Yeah.
it's just rigorous.
It doesn't bother me since it's not skipping over a rule to the right.
Right.
Alright. So that's the first one. A equals 1 implies b equals 3. Now you need to prove that a not equal to 1 implies b not equal to 3.
Okay. I'm just gonna go ahead and show that this is the same as this. It's the contra positive.
Right. So instead of dealing with the headache of showing that a not equal to 1 implies b doesn't equal 3, use the fact that we know that the contra positive gives you the exact same thing. So the rule that she's using is a implies b, alpha implies beta, is logically equivalent to not beta implies not alpha.
Right.
So that's what she did here. So we have alpha implies beta is the same thing as not beta implies not alpha. You see that?
tricky.
So using the contrapositive actually greatly simplified the problem.
Yeah, that was way easier than proving that.
So there was a nice example of where something like the contrapositive comes in hand.
Now it's gonna feel like we didn't prove it.
That is proved.
I know it's going to be proved.
It shouldn't feel that way. That was the breakthrough to solving the problem.
Yeah, that was like,
That's your
No,
aha
I
moment.
understand that.
Only because you took calculus.
No.
Laura, don't fall asleep. You were snoring a little bit. You're lucky the camera didn't pick it up. By the way, does Monday nights continue to work for you guys?
Talk to them, but they want to do singing on Monday nights, is what I heard today.
when, okay.
But I don't know about Tuesday
I thought
nights.
they were gonna do
Tuesday
or
nights.
Thursday.
Something's wrong with dental schedule for Tuesdays.
Tuesdays work for me, but Wednesdays or Thursdays work.
Wednesday's the only day I can't do.
Tuesdays,
What?
I am not
Done?
at seven.
Is there a third part?
Yeah. Just gonna look through real quick.
Yeah. but
So you
usually
started
we
with
got
that. 2a minus 3b minus 3, 0,
Which is
equals 2a minus 2, rewrite 0,
Right before choir.
a equals 1. Yeah.
what about Thursday?
Okay. So the last part was,
Thursday sucks. Then Monday sucks.
Okay, what is it?
what are the values of a and b if a is not equal to 1?
Just very thick, this and what you require to, that's gonna be input.
Right. Yeah, they were asking for us today.
A is not equal to 1.
Figure it out next week.
Alright,
And remember that a and b are integers.
alright. So, A not equal to 1 is gonna imply A equal to something and B equal to something. Do I have to find specific values for A and B? Or can it be like A is everything not equal to 5 or something like that?
I don't know if you're going to find specific values or if you're going to get a equals something in terms of b. But I wouldn't be surprised if we got specific values.
Alright, then I'm going to get the contrapositive of this now. Okay.
Prove that A.
So what's the significance of a not equal to 1?
Means b is not equal to 3, right?
That means that side doesn't go to 0.
Exactly. That means that this right here is not a 0.
Alright,
Which means using that term, this rule is legal.
Oh, yeah.
okay.
We were using that rule last time. With A equal to 0.
Is that,
Not gonna lie.
Oh no, A was not
Way
equal
to
to 0.
that looks like, is that 2a minus 3 on both sides?
No. It's 2a minus 3 on one side, 2a minus 2 on the other.
Oh, okay.
That'd be way too easy.
Yeah, it would be.
I would
So
say
you could add one and subtract one from the right side, couldn't you?
We can't subtract.
So if you're thinking about,
Add
oh,
one,
never mind.
subtract one from there, then cancel it out so that b minus 3 is equal to.
You're saying right here, you're saying rewrite this as 2a minus 3 plus 1. Then you don't have 2a minus 3 times something. Yeah, but plus something.
Oh, that's right.
Second off, even if you did have it times something, you don't know that you can get rid of it from both sides because you don't know that it's not equal to 0.
That's right, right.
All we know is that 2a minus 2 isn't equal to 0. 2a minus 3, who
I
knows?
would
It
say
could be
let-
0, so
let
we
2a
don't get to
minus
just do
2
that.
equal x. Then I substitute for x, and then x for equation.
You almost have the right idea, you're just looking at the wrong term.
I'm guessing I was supposed to find one of the variables in terms of the other. If this is all I'm given, right?
That's a 3, isn't it? Instead of 2 on the left.
Okay, now let 2a minus 2
2a
equal x.
minus 2 minus 1.
Oh, yeah.
Huh?
I would say this. I would say let 2a.
Oh, maybe that's not going to help like I thought.
I would say let 2a minus 2 equal x. And then solve for x, and then plug back into it.
I'll play with my idea on the side. You can keep guessing whatever you think
Yeah.
is the right way to do
Like
it.
I would just say let that term equal a term.
Yeah, you could do that.
And then multiply everything out, and then pull everything to one side. Now, can you do that with those rules?
Yeah, I bet you could. It'd be more roundabout, but you could do it.
Keep going then. I would multiply, I would distribute, oh, you can't distribute.
I'm just, if I can get x just in terms like just x alone, then that'd be useful, but I'm not sure if I can do that.
Right.
Like,
Oh, there's a thought. Just clean up the algebra. That's a good thought.
I could go ahead and distribute
Yeah, I try that.
the,
Exactly. I was thinking, keep going with it. You did exactly what I would try.
Wait, you can't do that. Distribute property, you don't get that roll.
Hey,
Yeah, you do.
Okay.
it's actually fine, because we have the flex property.
Now get all get all x to one side, and then factor it out.
There's a whole different bunch of terms.
That's tricky.
Now factor it out.
Whoa,
You can't
whoa,
do that.
whoa.
You can't do that.
what do I do?
What did you do?
How is that?
Minus
You
x,
saw me at.
she can do that.
I minus x, so that's
You
4x.
can't
Yes,
minus
you
x
do
from
it
both
like an
sides.
algebra problem.
Nope.
You gotta
You
follow
gotta use
the-
those rules.
You can
Oh,
go
I'm
from
sorry.
this to this.
It's
Do it.
hard
You
not
can
to
still do it.
use math. Okay.
You can still do it, just show it a different way, I'm sure.
It's, those rules are the exact same, it's just roundabout.
You're saying I can still do the same thing with
It's the same thing, you're just using those rules to do it.
Not really explain.
Adding something to both sides and canceling is the same
Explaining
as
and being
subtracting.
on track are two different things.
Okay.
I can be on track, but if I was trying to explain. Right. There you go.
Can you do that?
If I'm doing this, I'm gonna end up with, right?
Alright.
Which
You know,
doesn't
okay,
seem
so what you'll.
Maybe substituting x isn't the right way.
I think we gotta listen to the trick of A is not one. Obviously, that's going to take a proof from the very start to go from there.
Yeah.
A is not equal to 1. What does that mean?
Just keep going, right? Just gonna play with stuff.
If I'm going to use a not equal to 1, I'm going to use it in an implication so that I can somehow negate that statement.
You will have to find a value for A, I think. It will be a specific value.
I think it's gonna be one in terms of the other, seeing as how you have two unknowns and one.
I can't solve for A or,
Yeah, there's
or
no
B.
system.
Well-
It's two variables in one equation.
Yeah.
I know, but that happens in algebra all the time, you know, when you're solving like a...
But you have two equations usually, so that you can find
Yeah.
actual answers. There's no way that you can do this with just one equation.
You can find A in terms of B, B in terms of A, or the contrapositive of this, I'm going to negate that, which is but I don't know if
Wait,
it's
this
useful.
has got to,
Yes,
if it's
we're-
finding in terms of something else, this would be way easier. You could,
She doesn't like. It's the teacher going for it now. And then you're expected to go home and do it. You go, no, there's no way.
Now I'm not a calculus.
I'm trying to figure out how to do those rules, because
There we go.
usually you just
Question.
divide it on both sides.
That's true.
The answer was 3 and 1. Yeah, man. Nobody was saying it's for extra students.
Yeah.
I feel like it's gonna end up being something like, oh,
Of course it is. Always.
Don't you have to use information from your other
okay,
two
I'm
proofs?
excited, Donnie. Look, plus negative 1 to both sides of that equation.
Why?
If I did use that other information, I have
Because
A
then
not
you can
equals
cancel
1,
it out,
which
can't
means that B, we don't, like
If you
this
plus
won't
negative
work
one-
Means
because
B
A
does
doesn't
B
equal
equal
1.
3.
And if I used this, that's not true, which means that also has to not be true.
Right.
So
Okay,
if I'm using
Tell me if I'm
using
wrong.
this with these two, all I know is that B doesn't equal 3 and A doesn't equal 1.
But she doesn't know
tell
what
me if
A
I'm wrong,
equals one.
say on Donnie's right there. Plus
Okay.
negative 1 to both sides of the equation. So then you're gonna get B minus 3 plus negative 1 equals,
You can't divide it though, because then you have an addition instead of multiplication. You can't get rid of the term you're looking to get.
no, you'll have a term right there, and then you'll have a term right there.
Right, but you can't divide it, because then you'll have a negative 1 divided by x minus 1, and that's not huge.
No, it'll be x minus 1.
Look though, you'll have x minus 1 times b minus 3.
Right.
You can't use that rule though, if that makes sense. You can't use that rule because it
Oh,
would be
because all of a sudden,
ab plus 1, or minus 1.
right, you're saying, yeah. Stupid. I don't like this game.
I wonder if you could prove it by contradiction. Say let a equal 1, and then prove that. Oh no, that wouldn't work, because there's a, you're trying to find
You're
numbers.
right.
She did there.
Well, yeah.
No.
No, because it's
I mean,
wrong.
maybe just
Yeah,
getting
you
the
could prove by
answer
contradiction
first
if it
will help.
gave you an actual value to check it by.
Do they have an answer?
So let's just get the actual answer and then worry about doing it right. So,
That's a good idea.
2a
Like we were doing it
Probably
before.
should have just done that in the beginning.
b minus 3 is equal to 2a minus 1.
Two.
2. So we have 2ab minus 3b minus 6a plus 9 is equal to 2a minus 2. So we have 2ab. Here, I don't like the ab.
Pythagorean theorem.
What are we doing wrong that is obviously wrong?
Okay, make sure we wrote the equation right.
Rather than doing all that headache, let's just
Well, I
do
guess
this.
it has to be right. 'cause
b
of-
minus 3 is equal to 2a
Which
minus
means stop
2
at
over 2a minus 3. So b is equal to 2a minus 2 over a minus 3 plus 3. And we know that b is a whole number.
So now we have to get to that with.
And we know that a is not equal to 1. A has to be 0.
Why?
Because any other number, and you're going to get a fraction plus 3.
If a is 0, then you have to get a fraction plus 3.
Yeah, you do.
Oh, sorry. Oh, and a can't be 1.
Right.
So 1 would have given us 0 in the numerator.
Which would have given us b equals 3.
Would have given us b equals 3.
But it says b
But
is
a
not
is
equal,
not 1.
and b is not equal to 3.
What is another number a I can plug in there that makes so I don't get fraction?
Why
Six.
why are we so focused on making sure b is in a fraction?
It's
You're
not
going to
saying
have to
either.
use that information. So we know that a and b are whole numbers.
Does it said that?
Yes,
Okay.
6 would be.
because you're going to get, I'm guessing you're going to get b in terms of a,
It's always going to be.
where there's only one number a,
That's always
that's a
gonna
whole
reduce
number,
to
that
2
makes
base.
sense.
Because
To get b a whole number.
is
That's
always
what
going to
we
be.
have.
Right.
Yeah, but I must have done something, or I'm missing something. I have to think about this problem. I know we solved it last year, so.
You can go look at the video.
I didn't record that early on.
Um,
My first year didn't work. So we'll call it there. There's a problem for us to play with.
try to solve it this week.
See who can solve it. Anyone who solves it gets entry into the class.
Okay, then
So take your picture of the problem. You're trying to show, you're trying to figure out what a and b are if we know that a is not equal to 1.
And that's at the end of the section.
Or I guess if I can get this video uploaded quick enough, you could check on there.